Hello, this is Mr. B. Giriraju, Professor of EC Department, Engineering College, Hyderabad. So, in the last video, I have given explanation for the spectrum analyzer, logic analyzer, and fixed variable frequency AF oscillator. So, before going to start AF sine wave and square wave generator, once again I will recall previous topics. So, actually, what is the use of spectrum analyzer? So, with the help of spectrum analyzer, we can measure amplitude, time, frequency in frequency domain. That means here we can express values in x y axis in frequency domain. So actually here with the help of filter bank circuits we can send frequencies in the form of parallel filter bank. So here the output of the filter banks you can observe in the form of simultaneously overlapping outputs from 1 to n values. So you generally here you can observe two types of spectrum and lasers. One is the swept frequency analyzer and other one is the RF spectrum analyzer. So finally with the help of this type of spectrum analyzers you can measure voltages and frequency values time values in the form of amplitude. So next one, logic analyzer. So actually we have two types of logic analyzer based on logic state analysis based on logic time analysis. So these are the two methods to understand logic analyzers. So next one, signal generator. So with the help of signal generator we can generate square wave, sine wave and triangular wave for the different frequencies. So actually to build any type of generator we need the help of the oscillator and attenuator. Here oscillators are the sine wave generators and attenuator, with the help of attenuator you can improve the output of the oscillator. Finally we will get our required output in the form of RF signal. So actually to build any analyzer, so we need sine wave generator. So actually this is the basic set of the sine wave generator that having some set frequency in the form of oscillator and attenuator is the set level. With the help of output of the set frequency you can adjust with the help of set level. Finally you will get output in the form of RF signal. So this is the modern laboratory type signal generator. So now I will going to explain AF sine wave and square wave generator. So this is a basic block diagram of the AF sine wave and square wave generator. So actually in this figure, so we are having first block as the Wien bridge oscillator. So actually here Wien Bridge oscillator is the best for audio frequency range. So here signal generator is called the oscillator. A Wien Bridge oscillator is used to as a signal generator. So with the help of Wien Bridge oscillator, we can generate a sine wave. So that output of the Wien Bridge oscillator goes to the function switch. This is the function switch. So the function switch directs the oscillator output either the sine wave or square wave shaper. So after performing operation, you will get at the stage of sine wave amplifier and sine wave, square wave shaper. So you will get the output in the form of square wave. So now, by the using attenuator, circuit can vary the output. So here this instrument generates a frequency range from 10 to 1 megahertz. So this generate frequency range from 10 to 10 hertz to 1 megahertz. 1 megahertz frequency range. So now the output of the sine wave amplitude can be varied from 5 millivolts to 5 volts. 5 volts. So it is in RMS. So the output taken to the push-pull amplifier. So here at the stage of attenuators, you can observe push-pull amplifier. So for low output, the impedance is 600 ohms. 600 ohms. The square wave amplifier at this stage can be varied from 0 to 20 volts. 20 volts peak value. 20 volts peak value. So square wave can be adjusted from 30% to 70%. 30% to 7%. So actually a square wave, so to generate square wave you should maintain duty cycle as 50%. Suppose that may be below 50, you can call as false wave. So more than 50 also false wave. So to generate square wave you should maintain duty cycle 50%. So exactly. So the instrument requires only 7 volts power at 220 volts and 50 hertz. So actually here square wave and pulse generator along with CRO. So based on change in duty cycle. So you can study output of the sine wave shaper. So actually the instrument requires only 7 watts of power at 220 volts and 50 hertz. So this is the idea about AF sine wave and square wave generator. Finally, we will get at the output stage of sine wave amplifier, we will get sine wave, and output at the stage of square wave shaper, so we will get square wave. So this is the idea about AF sine and square wave generator. Now I am going to discuss square and pulse generator. So actually here square wave and pulse generator along with CRO used. So measuring instruments. So actually this is the square and pulse generator. So here you should maintain some upper current source and lower current source that give to some switching circuit, and after that you can observe some schematic trigger. So with the help of schematic trigger operation, so you can generate either square and pulse generator. So here the basic difference between square wave and pulse generator is concerned with ratio of pulse width to the pulse period, that means duty cycle. The duty cycle of a square wave generator is 50% and duty cycle of pulse generator varies between 50 to 90%. So here this figure shows the basic block diagram of square wave pulse generator. So it contains two constant current sources, a simple switching circuit, and schematic trigger and ramp capacitor. So actually this is the basic components to generate square wave and pulse generator. So actually here as the ramp capacitor charges, the ramp voltage increases linearly. So you can observe current I1 and I2, so like this. Finally we will get our required ramp. So voltages are like this. So as soon as the positively increasing ramp approaches predetermined upper limit that is set by the internal elements of the circuit, the schematic trigger changes from one state to another. That means here we are having constant current source and upper state and lower stage. So now with the help of schematic trigger you can change position of the switches. So here the schematic trigger can be bistable multivibrator. So when the schematic trigger changes the state, its output goes to negative and the current switches reverse the condition. So and the ramp capacitor discharges slowly. Now the lower constant current source control this discharge. So when the schematic trigger change its state, output goes to negative. output goes to negative, the current switch reverse its condition and the ramp capacitor discharge linearly. So discharge linearly. So now the lower constant source control the discharge rate. So the complete process will be repeated and negative pulse are produced at the output at a constant rate. So here the output schemic trigger is applied to the 600 ohms and 50 ohms output amplifier. So the duty cycle of output waveform is determined by the ratio of current I1 and I2 and is controlled by setting up symmetric control. So here the ramp capacitor size is chosen by multiplier switch. The multiplier switch and frequency control provides decade switching, and the frequency range of this generator is covered in 17 decade steps from 1 Hz to 10 megahertz. So at the stage of capacitors, we will get our required waveform is like this. So by the controlling I1 and I2. So observe here I1 is the constant current source and this is the upper stage, and I2 is the current constant current source, lower state. Both operations depending on the switch based on our requirement. So this is the output waveform for square end pulse generator. So next one, function generator. So here everyone knows side about the function generator. A function generator is a device that can produce various pattern of voltage at a variety of frequencies and amplitude. Actually here this is the function generator instrument. So this having paint panel like this. So you can observe some probes, points and potentiometers are like this. So with the help of potentiometers and potentiometers you can vary so position of the amplitude, voltage, so like that. In the same you can vary amplitude also. So this is the print panel of the function generator. So actually it is used to test the response of circuits to common input signal. The electrical leads from the device are attached to the ground and signal input so of the device under test. So these are the probe points. Now with the help of these probe points you can connect our required measurement quantity. So you can call it measuring. So most function generators allow the user to choose the shape of output from the small number of options. Generally with the help of function generator you can generate waveforms in the form of square, sine, triangle, like that. A square wave signal goes directly from high to low voltage. Sine wave, the signal curves like a sinusoidal from high to low voltage. Triangular wave goes from high to low voltage at a fixed rate. So the amplitude control on a function generator varies the voltage difference between the high and low voltage of the output signal. The direct current offset control so on a function generator varies the average voltage of a signal relative to the ground. So this is the block diagram of the function generator. So observe here. So actually this block diagram having frequency control. This is the frequency control, this block. So this regulates two current sources. One is called upper constant current source, and other one is called lower constant current source. So your upper current source supplies constant current to the integrator. This produces some output voltage that is increasing linearly with time. So increasing linearly with time like this. So lower current source, this one, supplies reverse current to the integrator so that output decreases linearly. So with time. So now I will show function of the function generator in the video form.
Discussing two apparatus being used in electronics.
So this is the function generator.
The first apparatus is called the function
So these are the
which is used to generate signals.
print panel of the function generator. We can see
which is an eye of an
output of the function generator and CRO like this.
We can see here right now.
So this is the probe.
In this panel,
you can observe
frequency
values on the display
what kind
like
of signal
this.
is this? SIN. SIN means a sinusoidal. Then what is the amplitude? This thing denotes the amplitude.
So you can maintain sine wave. This is the frequency.
Now, if you want to
maintain like this.
Frequency. If you want to change the frequency and can change using this.
So with the help of
so it is becoming less, it is becoming more.
So this control you can vary positionally
to 1000 hertz.
Signal.
Now change it. Next, if I want to change the amplitude.
So these are the selected frequencies.
2 volts. If I want to change the same knob.
So you can change the amplitude of the waveform like this.
So right now the unit is in volts.
This knob.
If you want to make this unit in millivolts, you have to divide by 10, multiply by 10.
So you can change the decimal values also like this.
If you divide it by 10, now you can see your unit became millivolts. Now let us come back to volts when I press this into 10. When I press this into 10 one more time, you see the point from
you
here
can set
move to
values according to our requirement.
So right now
based on the operation.
2 volts and having the frequency 1 hertz.
Or like that.
Now what is the function? My function.
So in the same we can change frequency with the frequency factors.
Like
these are the point or representation of the frequency values. Values according to our requirement.
2 volt again 1 gram minus 2 volt means a negative gram. This is pulse 1 volt because when we say pulse.
So finally we can observe
reference to upper level or reference to below level.
On
when I press it again,
CRT screen.
Minus 1 volt means below. Then a DC voltage. Then again back to the sinusoid. So right now we have set it for a frequency of 1000 Hz for an amplitude of 2 volts.
So when I press the switches, you can
now,
change
when I connect this
frequency of the
this written as output, you might have seen here.
Output.
For your convenience.
This is the probe.
It's written output. Whatever is generated from this,
so from this point, you can connect it to our required circuit diagram.
So important.
That means you can provide this signal to input of the other device. There may be either sine or square, so like that.
Into 10 or divided by 10, you can use this. So now this signal what has been generated from the function.
So this is the operation of the function generator.
Here discussing
so you will get finally waveform. So in this form. Is for
Reverse
sine wave
apparatus is
only.
called the function generator, which is used to generate signals.
So actually in the so block diagram. So here you can observe integrator. So that the integrator output is given by, so V naught is equal to, so my 1 by C integral 0 to T IDT. So IDT. So here C is the capacitor value, and this is the time, charging and discharging time, and I is the current with respect to time. So this is the output of the integrator. So you can observe like this. So here frequency is controlled by varying upper and lower currents. An increase or decrease in the current will increase or decreasing the slope of the output voltage, hence controls the frequency. So here the voltage comparator change state set a predetermined maximum and minimum level of the integrator output voltage. So when the predetermined level is reached, it changes the state and switches the current source. So this produces square wave. So like this. So depending upon the operation of the integrator with the help of upper constant current source and lower constant current source. So here the integrator output is generally triangular wave, whose frequency is determined by the magnitude of the constant current sources. If the comparator output device is square wave, this one of the same frequency. Here the resistance diode circuit delivers a sine wave from the triangular wave with less than 1% distortion. Actually here at the stage of integrators you will get output in the form of a triangular wave. So now passing through the resistance diode network, this produces a sine wave. So actually this sine wave from the triangular wave with less than 1% distortion. So here actually this is the operation of the function generator. So actually every function generator having some print panel. So now I am going to explain print panel controllers. These are the print panel controllers. Okay, now I will use some details about the print panel controls of the function generator.
Here discussing.
So actually first you can observe frequency selector. So it selects the frequency in different ranges. So where is the frequency in the range? 1:11. Scale is nonlinear. Frequency multiplier selects the frequency range over the 5 decades from the 10 Hz to 1 MHz. So amplitude multiplier attenuates the sine wave in 3 decades by into 1 into 0.1 into 0.01. So with the help of these values, we can estimate our required value of the waveform. So variable amplitude attenuate the sine wave amplitude, continuous symmetry control. So these are the front panel values. So in the same way, you can observe function switch. Select either the sine wave or square wave. Output available. Provide sine wave or square wave. So synchronicity is used to provide synchronize of the integral signal with an external. So signal on off switch. So these are the front panel of the controllers. So here with the help of on off switch, you can on off a function generator. So these are the front panel controllers. So now I am going to explain sweep frequency generator. So this is the block diagram of the sweep frequency generator. So actually this block having ramp generator and voltage tuned oscillator. This is the ramp generator and voltage tuned amplifier. So actually here with the help of sweep frequency generator, process of testing the frequency response of the amplifier and filter can be done by signal generator, so that automatically varies its frequency over a predetermined range. This instrument is called a frequency generator. So actually here we have one block diagram for the frequency sweep generator. So like this. So this is having the first block ramp generator and one amplifier. So you can call it as differential amplifier. This is the differentiator and the VTO, and this is the LC control, and this is the voltage gain amplifier and control attenuator. So these are the basic blocks in the sweep frequency generator. So with the help of the generator, so you can generate predetermined range. So frequencies, sweep frequency. So values are like this. Actually, this is the setup for block diagram of sweep frequency generator. So now I am going to explain arbitrary waveform generator. So this is the basic block diagram for arbitrary waveform generator. So actually this having first block as digital to analog converter and one clock generator. This is the processor and memory sequencer and low pass filter. So finally you have to take output from this block. So you can observe some markers also like this. Okay, next now I will give about memory. Here memory, a digital representation of a waveform, is loaded into AWG memory through the variety of software applications. Here AWG stands for arbitrary waveform generator. So is loaded into AWG memory through a variety of software applications such as the MATLAB, LabVIEW, Visual Studio Plus, so IVI and SCPI. The memory is clocked at highest sampling rate supported by the AWG. The size of the memory will dictate the amount of signal playback time available. So the rule of thumb to determine the playback time is memory depth divided by the sample rate equals playback time. The faster your sample rate, the quicker you will use the available memory. So next one, sequencer. So this is the sequencer. The sequencer circuitry can solve memory depth limitations by arranging sequencing. So the waveform into segment to create your desired waveform. So memory sequencing or memory ping pong does this by only enabling memory during critical waveform. So portion and then shutting off. So you can think about it like this: when the round of golf imagine how much recording time you would save if you only recorded the players striking the ball and not all the walking and setup time. The sequencer does the same thing by only recording waveforms, transitions and not ideal time. Synchronization is maintained by the trigger generator which enables the waveform. Trigger events can be internal, external, or linked together, linked to another arbitrary waveform. So this is the second block. So third one, markers and triggers. So these are the markers and triggers. So marker output are useful for triggering external equipment. Trigger inputs are used to alter sequencer operation. So instead of this, you will take help of this one. So resulting in the desired waveform entering DAC. Here, hardware or software triggers can be used for applications requiring exact timing like wideband signals. They can also be used where multiple arbitrary waveform generators are synchronized together and need be triggered simultaneously. So next one, clock generator. So here the timing of the waveform is controlled by an internal or external clock source. Internal or external clock source. So the memory controller, this one, keeps track waveform events memory and then outputs them in the correct order to the DAC. So the memory control saves space by looping on repetitive elements so that the elements are listed only once in the waveform memory. So clocking circuitry controls both DAC and the sequencer. DAC and sequencer. So next one, DAC, digital to analog converter. So here waveform memory contents are sent to the DAC. So here digital voltage values are converted into analog voltages. The number of bits within DAC will impact the arbitrary waveform generator's vertical resolution. The higher number of bits, the higher the vertical resolution and the more detailed the output waveform will be. DAC can use interruption to reach even higher update rate than what was supplied by the waveform memory. So this is the function of the DAC. Low pass filter. So this one, because the DAC output is low, so actually this output is a series of voltage stage steps. It is harmonic and requires filtering for a smooth sinusoidal analog waveform. So last one, output amplifier. So after the signal passes through the filter, it will enter an amplifier. So the amplifier controls both gain and offset. This gives your flexibility to adjust output gain and offset depending on your application. For example, you may need high dynamic ranges for radar and satellite solutions, or high bandwidth for high speed and coherent optical solutions. So these are the block diagram of the arbitrary waveform generator. So now with the help of this generator, so you can calculate solutions of high bandwidth for high speed and coherent optical solutions. So I will continue remaining topics. I will continue in the next class. Thank you.